Kerala, and then right after his undergraduate, if I understand it, he went to Syracuse for his PhD. He worked there with A.P. Balachandran, and the work they did there was on the SCUM model. And they were the, if I remember correctly, they were the first people to show that skirmion can be quantized as a half integer with a spin half integer, and so can be identified as nucleon. Subsequent to that, he was a postdoc at the Institute of Advanced Study, and then at ITP in Santa Barbara, ITP now known as KITP. And after that, he was a professor. He was a faculty member at Columbia, and in 1993 he moved to City College of City University in New York, and he's been there since then. And those of us who have followed some of his work, and maybe many of you have, so Parameswaran has been interested in a large number of topics. He's worked on solitons, he's worked on index theory, he's worked on aspects of non-commutative geometry. But when I look at the kind of work he has done, it seems to me that his first and enduring love is for QCD, and it is in that spirit that he is going to tell us about some work that he has been doing over the last maybe 5-7 years.
A little more than that, actually.
More than that.
Yeah.
And along with his collaborators, have done some very nice and very precise work on exploring the idea of confinement in 2+1 dimensions. And there are important lessons for us for what we learn from 2+1 to apply to 3+1. So when I say 2+1 and 3+1, I mean nonabelian case theory in 2+1 and nonabelian case theory in 2+1. So welcome, and we look forward to listening to you.
Thank you, Sachin. Well, thank you all, and thank you to the Institute for inviting me, and especially to Sachin. It's very nice to be here. I think I was here many years ago, perhaps before some of you were even born. But it's good to visit the Institute again, and I see that it's a very active, very interesting place. So thanks again for the invitation. I'm going to talk about confinement as advertised, spread over 4 lectures. The idea is to try and do things in some detail, as well as go over perhaps some things in a little more pedagogical way than a seminar would do. So I'll try my best, but please, if there are questions, stop me anytime. We'll go over it. The purpose is to try and convey as much as possible. So feel free to stop me anytime. Because it's a long and complicated topic, and confinement has been an issue for 50 years, we still don't have a proof of confinement. So one might say it is still an interesting problem. There are many facets to it, many ways of looking at it, and I don't think I would be able to cover any of that stuff in any detail. I'm going to zero in on a particular kind of way of looking at it that I've been following. But of course, to prepare the ground for that, I'll have to go over some general stuff as well. Okay, so I'll start with some general things today and then progress on to more specific calculations. So just to give a sense of, because there are 4 lectures, just to give a sense of where we are going, I want to tell you a little bit about what we are going to talk about. Okay, so I'm going to start today with just setting up the basic framework for quantizing gauge theories. Of course, we are talking non-abelian gauge theories mostly. I'll talk about the Hamiltonian formalism, which is not very often discussed, or if discussed also, it's not very often used in actual calculations. But that's what I'll focus on. I'll talk about the Gauss law, physical states, and how to define charges. Because one of the problems that we encounter the moment we say confinement is, what exactly is it? How do you define it? Okay, even that is something of a problematic issue, and there are no really good workable definitions, if you like, of what confinement is. And I want to convey to you some of the subtleties involved in defining what is confinement. Then I am going to talk about what is the configuration space for gauge theories, which is often referred to as the gauge orbit space. Everything I am going to do is pretty much based on the structure of the gauge orbit space. The point of view that I would like to pursue is that when we set up the problem, any quantum problem, the nature of the space in which it is formulated makes a lot of difference, and in fact probably carries actually can tell us a lot about the actual physics of the problem. Okay. So that is the kind of, so it is important to understand the nature of the configuration space, by which I mean both the geometry and the topology of the space. And once I have that, I can talk about confinement, what is the definition, and how do we set up some sort of diagnostics for confinement. And that's sort of the general introduction, and then I would try to go on to the 2+1 case, and I will talk about parametrizing gauge fields in 2+1. Why is that important? It's fairly straightforward to see that, you see, we often think, correctly so, that whatever physics we do should be independent of coordinate systems and should be invariant and so on. That's nice, but try and solve the Schrödinger equation for the hydrogen atom in Cartesian coordinates. You will find that it's not very easy. Okay. So although results can be independent of coordinate systems, it always helps to be able to choose coordinates in a nice way that you can make the problem solvable. Okay. Like we do polar coordinates for the hydrogen atom. Coordinate choices are important, and in the language of fields, that means a particular parametrization of fields is going to simplify things for us. Okay. So that's what I will do. Once I have that, I can actually set up the problem entirely on the gauge orbit space, solve the Schrödinger equation, and I will derive an analytic formula for the string tension in 2+1 dimensions. Okay. And there will also be another analytic formula for Casimir energy that I will show, and I will compare these results then with the lattice analysis. Okay. So you can actually make very specific predictions. Of course, when we talk about analyzing the theory in terms of the Hamiltonian formulation, we are talking about Hamiltonian operator, wave functions, things of that sort. Not very often discussed in a field theory context, but that's what I want to do. So there are wave functions that you can look at, other types. I mean, after our work, other people came up with proposals for wave functions. I will comment on that. And then I will talk about a number of other issues related to that, string breaking effects, Chern-Simons theories, and entanglement issues, and so on. Okay. Okay, this is probably towards the end of this. I'll go back to 4 dimensions, talk about dual superconductivity a little bit, and how you can set up the general problem of confinement in 4 dimensions, and again look at the gauge orbit space in 4 dimensions and tell you a little bit about the geometry and topology of the space. Okay. So that's the general idea of where we are going. It's a lot of material, but I'll try to be as elementary as possible, and please, as I said, do stop me with questions if you have any. Okay. Now, most of the original work that I report here is done with Dimitra and Abhishek. They're both here. Chanju Kim, Yelnikov, and Antonina. These are my collaborators. There is a review that I wrote recently on the 2+1 case, just came out last August, which you can find on the web, which pretty much contains, at least as far as the 2+1 dimensional analysis is concerned, pretty much everything should be there. Okay. All right. So let's talk about setting up the theory. Very elementary starting point. We consider some matter field, a bunch of them. Psi I takes values 1 to n, so it's some n-dimensional representation of some Lie group G. So it's like the matter field that we talk about. Could be fermions, could be bosons. It doesn't matter for us at the moment. And if you want to construct a theory with local symmetry G, so you want to make this into a local symmetry, we all know how to do that. We start with the definition of covariant derivatives like so, where we introduce the gauge field A mu, which covariantizes the derivative. Okay. And the gauge field is a matrix valued in the Lie algebra of the group G, and it transforms under gauge transformations like so. Okay, it's an inhomogeneous transformation. There is the G A mu and G inverse, which is homogeneous, but there is the inhomogeneous piece here. Standard gauge transformation that we normally do. Okay, and of course, once you have the covariant derivative, by definition, if you take the commutator, you are going to get something covariant. That is your field strength tensor, which, if you write out in components, has this form. And this is the Lie algebra of the T matrices, which are generators of the group. So that's a basic framework. This is something which everyone learns in elementary, first semester of field theory or whatever, right? So this is all standard stuff. The field strength tensor F mu nu transforms homogeneously under gauge transformations, gets conjugated by the transformation matrix G. And then once you have these ingredients, it is easy to write down an action. If psi is a fermion, I would write a covariant derivative with gamma matrices. So here is a Dirac action, here is the action for the gauge field. Okay. So that's a standard thing that we all know and we talk about. The second term here, again I explicitly carried out the trace to write it like so. This is the so-called Yang-Mills action, and this is the Dirac action. Okay. So, and of course F mu nu is what is given here. Okay. So why is this interesting? As a, at the end of the day, after all, we are doing physics. So why is this theory interesting? It's interesting without any further additions to this theory. It's interesting because if we take G equal to SU3 and psi represent quarks in the fundamental representation of SU3, this is quantum chromodynamics. It describes the theory of strong nuclear forces. So that is the real physical point. But of course, free quarks have never been observed. Extensive searches were carried out in the 70s and so on. No one has observed free quarks. So that led to the idea of confinement, that you cannot see free quarks. So the question we want to analyze here is, what is confinement and how can we understand that? That is the basic tenor of my talks here. Okay. So as I mentioned before, I will be following a Hamiltonian approach. So I'm going to write the action in a form that's more conducive to the Hamiltonian analysis, separate the F square term into an E square type term and a B square type term. This is the usual E square minus B square formula that we write. And then of course the E field involves time derivative of A and various other terms added to it like so. And B, whether it's 3 plus 1 or 2 plus 1, they have similar structure, but in 2 plus 1 of course B is a scalar. Okay. The equations of motion are given by these evolution equations for E and then the Gauss law, which is this condition here. Okay. These are just the equations of motion for the theory. Okay. The Hamiltonian can also be obtained by simply taking the energy moment tensor, integrating it over all space, and you get that. Okay. The important thing for us to set up the Hamiltonian formulation is that if you start with this action, then I can look at the terms of the time derivative and I can write down the canonical 2 form that is involved in the quantization. Okay. You may recall that if I have a theory with an action S, then I look at the variation, then it is a structure of a bulk integral over the volume times some variation of the fields. And then there is a boundary term we can write, which is of the form, let me call it alpha, at the final time slice, you going from initial time to final time. Then there is a surface term that we normally write like this, and this surface term alpha, this defines a canonical 1 form for the theory, which means it is the analog of the PDQ in particle mechanics, and its variation gives you the canonical true form. Okay, so that tells you how to set up Poisson brackets and commutation rules and so on. Okay, completely straightforward thing to do. Okay, so why are we doing that? Because once I have that, I can set up the commutation rules. There is no canonical momentum conjugate A naught in this theory because there is no time derivative for A naught. Therefore, we can choose A naught to be 0, and then these are the basic commutation rules. Okay. They just follow from just reading off from here. You can see that that's what we need. Okay, the equations of motion, now we had to rethink about it because the Heisenberg equations of motion or the Hamiltonian equations of motion talk about time derivative A and time derivative E, but there is no room to derive Gauss's law as a Heisenberg equation of motion. Okay, this is part of the equation of motion defining the theory, but we do not have, it doesn't appear in the form of time evolution or something. Therefore, you cannot derive it from the usual Heisenberg equations of motion. Notice also that E is part of the initial data defining the theory because it's a phase variable. Therefore, del dot E equal to 0 means the initial data is constrained. So that constraint is has to be imposed in addition to everything else we do. Okay. So the whole issue is about how to impose this constraint. Okay. So let's take this Gauss law operator multiplied by some function theta, integrate and define this operator G0 of theta. Okay. That's a Gauss law operator for the theory, and one way to impose this is to say that all the wave functions I'm talking about describing physical states will obey this condition. Okay. But the moment we say that, there are issues that we run into. One is that if we are going to impose this condition, we must also have the commutator of two such things vanishing. Otherwise, we'll have an inconsistency in the theory. So if you look at the commutator of two such operators, all we have to do is to simply go back to the previous line and look at this covariant derivative here. There is a pi, which is the electric field. The covariant derivative also involves an A inside, the capital D. And if you just simply work through the commutation rules, you see that this is what we get. Okay. So the commutator of two such operators again reproduces the same kind of operator with a different parameter, but there is a surface term that is produced in that. Okay. So consistently imposing Gauss's law means this surface term has to go to 0. That puts a constraint on the type of functions theta and theta prime, the test functions in the theory that I can use. Okay. So yes, theta is just a parameter. It is of the nature of a group parameter for the transformation, but at this level you can even simply think of it as, remember, whenever I have operators in the theory, because it's a field theory, I should think of it multiplying by some test function and then imposing, a condition like this can be imposed with arbitrary theta put in here, and the nature of the test functions will determine the operator nature of this condition. Okay. So it is, so you have to always choose a test function like that, because operators at a single point, that is not a very well defined concept. So you always try to smear it with some test function and then see what the properties are. Okay, that's what theta is. It's a function of x. Okay, all the coordinates in the problem. Okay, is that okay? Okay, so we realize that to impose Gauss's law consistently, we may have to require that on the boundary, which may be the boundary of space itself, we have to have theta going to 0. So this term drops out, whichever theta or theta prime or both of them going to 0. That's what we need. But there is another way to think about this also. It doesn't have to be just this equation that I said. You can also see this by looking at how we define functional derivatives consistently. Okay. So for example, take a functional which is integral of a square, commute with g0 of theta, And just from the commutation rules, from the fact that G0 involves covariant derivative of the electric field, you can see that it has this form. Okay. I'm just using a U1 theory here just for simplicity, but this goes through for any theory. And then once you have this right hand side, you realize there are two ways I can proceed. I can integrate over y first. D dx doesn't bother with the y integration. So I will get this equation. The right hand side simplifies to theta multiplied by d dot a, which if I do an integration by parts has this structure. Okay. At the same time, I can also look at d dx on the delta function, change the x derivative to y derivative, and then integrate over x, you get this. These two do not agree, and they can only agree if I require this to vanish, which means I will need theta to be 0 on the boundary. Okay. So generically, if you want to define functional derivatives consistently on any functional of A, you can only do that by restricting theta to vanish on the boundary of your region of integration. Okay. So that's given to you, and that argument applies both for the abelian theory and the non-abelian theory as well. Okay. So this is a big factor, because that tells us that you cannot impose Gauss's law with any test function that you like. Okay. Okay, let's take another step. So what happens then if I have that? Let's now look at a different transformation, which is I consider an element of the group, which is G here, element inside the group, but I'm going to take it to be constant over all space, but not necessarily equal to 1. So this transformation I'm talking about doesn't vanish or doesn't become identity at infinity or on the boundary. Okay, it's constant everywhere, and I choose it to be a constant different from identity. So then the transformation of A and E are simply this conjugation operation, because there is no derivative to be taken. G is constant, and that's what we have. Okay. Now, so this is not part of what is eliminated by Gauss's law, because this does not produce any equivalence a la Gauss's law, because G does not go to identity at infinity. Okay. So now what happens with this? Okay, it's trivial to see that if I take this transformation and put it into the Hamiltonian involves E square and B square, invariant combinations. I had it somewhere here. If you look at this, for example, you see that that's trace of E square and trace of B square, so it is invariant under the conjugation operation. Therefore, this is obviously a symmetry of the Hamiltonian. The Hamiltonian is preserved. It's also a physical transformation because it commutes with the Gauss's law. If you take the Gauss law I previously mentioned, all it does is to rotate the theta parameter to a new value theta prime, like so. Okay. And if theta vanishes at infinity, so does theta prime, so there is no problem with any of these things. Okay. So once I have this structure, then you can ask, what is the symmetry that is being generated? It's like an ordinary symmetry that you are familiar with in quantum mechanics. It's just an ordinary Noether symmetry. Okay. So therefore, I can argue that states must be classified by this symmetry. Representations of this symmetry would tell you what the states are. Those are the charge states of the theory. Okay. So we can introduce charge states by this argument, and we see that they should exist. There is no reason to rule them out. They are physically acceptable because everything is consistent with Gauss's law. The fact that we have this requirement here tells us that if I start with a physical state where which Gauss law gives me 0, then acting with this symmetry doesn't change the nature of the state. It still remains a physical state. Okay. So given that structure, we can then ask what are the charge states and what is the nature of these states. There is a slightly different way to slightly more general way to define this, which is to say that I look at this operator g of theta written like this. Notice that this is different from the structure of Gauss law that I did earlier, simply in the fact that the derivative now goes on theta rather than on pi. Okay. So it looks like an integration by parts has been done. but I am not going to insist that theta goes to 0 as x goes to infinity. So, this is a more general operator. It differs from G naught by a surface term, as I mentioned before. So, basically by integration by parts you can see that. And if I look at how it commutes with various operators, like for example A, it does an infinitesimal gauge transformation. Okay. But this transformation does not necessarily go to identity at infinity. But the good thing about this operator is that its commutator gives you a closed algebra. There is no surface term needed, nothing shows up. This is exactly closed by using this form of G. Okay. Further, G theta on psi is a physical state because G theta commutes with G naught. Okay. Why? Because G naught has a parameter which vanishes at infinity. The lack of commutativity which is in this term will vanish from the physical state. So, therefore, it is a physical operator. So, that means if you give me any state psi, I can act with G of theta, where theta does not vanish at infinity, and generate new states which are also physical, and these are the so called edge states of the theory. Okay. These are physical degrees of freedom that live on the boundary of your space. Yeah. I'm sorry. A charge state. So, this one edge state. Oh, previous slide. Sorry. Yeah. Yes. So the charge states are. So let's say you look at all possible states generated by the action of various fields on the vacuum. Okay. So some of them can carry charge in the sense that they respond non-trivially under this global rotation by G. Okay. So you act with the transformation which is originally the Lie group G, and you ask how do things transform under that. If there are states which transform non-trivially as non-trivial representations of the group, those are the charge states. Okay. No, charge states. So first you have all possible states you can construct in the theory. You impose Gauss's law, and you get the physical states. Among the physical states, there are still charge states, and the reason for that is because the global rotation is consistent with Gauss's law. That's what I was trying to argue here, that it weakly commutes with Gauss's law. So if Gauss law annihilates a state, so it is physical, it will remain physical after a rotation by this G. Okay. So charges are still allowed by the Gauss's law. There is no reason to throw them out. Okay, they are there. Okay, is that clear? Okay. So, but what we are saying now is that in principle you can have additional states which are essentially associated with the edges of your space itself. Okay, those are these edge states, and that's a more general construction. And this operator G here and the algebra, they generate you can exponentiate it and generate a group which I think is called the sky group in work that Sachin and Balachandran have done. Okay. So this is a more general framework within which the charge states also exist. Okay. So a priori we have no reason to rule out charge states in the theory. Okay. But then the question of confinement is really about what are there really physically charged states in the spectrum. Okay, that's a dynamical question. The quantization rules, as I have explained here, do not rule them out a priori. That is important. Okay. So I'm going to come back to that question in a minute, but let me just phrase this in a slightly larger framework. So we want to define certain spaces within which we can formulate this question more precisely. Okay. So let me start with the following object here. I'm going to look at the space of all gauge potentials I will need some mild conditions on that. You can talk about, for example, the curvature going to 0 at infinity. That's a kind of condition you can impose. You can impose conditions on integrals of f square and things of that sort. There will be some mild conditions that one needs to impose. But other than that, I am going to take the space of all gauge potentials. Of course, the gauge potential depends on x. So, when I say space of all gauge potentials, that is obviously an infinite dimensional space that we are talking about. Okay. I am also going to introduce another space which I will call G star, which is a set of these group elements. X is a coordinate in space. So, G of x is a map from space into the Lie group G, but we are going to insist that G goes to 1 at infinity, because that is what Gauss law told us. Okay. The only thing that Gauss law tells us is that we must impose theta going to 0 at infinity. Okay. So this is this group, this set here, G star, this expresses the redundancy in the theory, where you can say that two configurations are equivalent if they differ by the action of G star. Okay. So what it means is that, you know, our variables to begin with are the gauge potentials, which we, well, it's somewhere here, we talked about it. It's all formulated in terms of the gauge potentials here, right? These are the gauge fields, and those are our dynamical variables of the theory. And then once you have them, because there is equivalence under Gauss's law, we have to say these physical configurations are then given by this space modulo this gauge transformation space. Okay, this is a space of gauge transformations. So the configuration space is given as A mod G star, and that has an obvious fiber bundle type structure. Namely, I can think of A as a bundle where G star acts and you quotient to get this. Okay. So that is the configuration space that we are going to be talking about. Okay. So when you talk about a gauge theory, that is where it is formulated. Of course, if you give me a particular A and I do a gauge transformation by various G's, all the G's that I can put here together produce for a single A what is called the G star orbit of A. Okay. So therefore, this space which identifies all the A's which differ by gauge transformations as in this formula. So this space C is called the gauge orbit space. Okay. So it's only counting just the orbits, not points along the orbit by the action of G. So wave functions, because they obey this condition, that is saying that we can factor out G star, and therefore wave functions are really living on this space C. Okay. Now technically, of course, it's a complicated space. It's not something that I can cover. It's not like a flat space or anything. Therefore, I will need many coordinate patches to cover it and so on. So technically, wave functions are sections of a line bundle rather than just functions in the mathematical sense. Okay. But other than that, but what I am trying to emphasize is that all the action in the gauge theory happens on this space C. That is where everything is going to happen. Okay. So let me, however, make a couple of comments. I glossed over something that is called the reducible connections, and that arises from the fact that sometimes for specific A's, I'm not, pick a particular A, and then you might find that if I do a gauge transformation, there are certain A's and certain G's for which I reproduce A. So these are like A's which are unchanged under a gauge transformation. That can happen for specific A's. Okay. Generically, that is not the case, but it can happen, and G is not necessarily identity. Of course, if it is identity, this is backwards. Okay. So such potentials are called reducible connections, and the problem with that is if you try to quotient by gauge transformation, you know very well what happens if it's like, think of taking the plane and I want to do angular rotations and quotient by angular rotations. What happens? The origin is unchanged under angular rotations, and when I quotient, I get a singularity, right? My manifold ends there, and there is So I don't have a nice manifold one side quotient. Okay. The same issue happens here. This can lead to singularities. So one way to deal with that is to exclude reducible gauge fields. Simply take A to be space of irreducible gauge fields. Okay. To some extent, I have done that already by saying that my gauge transformation should go to identity at infinity. Okay. But another way to do that is to exclude these reducible gauge fields by hand and look at the remaining space. If you look at the remaining space, A mod G star, you can show is a nice smooth manifold. In fact, it has a nice principal G star bundle structure. And the good thing about it is that this A is dense in the space of all connections, which means that even though you have reducible connections and you exclude them, you are not losing much because they have effectively zero measure. Okay. So that's the idea. So these two results were shown by Singer sometime back in the late 70s, early 80s. And therefore, most of what I am going to talk about, if you want to think of the placement of this in the larger framework, we are talking about this space, which is space of irreducible gauge fields, modulo gauge transformations. Okay. So that's a space where all the things are going to happen for us. Okay. Now that's not to say that reducible connections are things you can completely ignore, because there are good reasons to believe that they have some important things to tell us about the theory. Why? Because if I look at a gauge invariant functional like the Yang-Mills action and look at its critical points, which are solutions to the equations of motion, then there are solutions which are reducible connections. So if you are trying to do a semi-classical expansion of your theory, that's what you will be dealing with. So it's not like you can just ignore them completely, but in the larger framework of looking at wave functionals on the space, they are not playing a major role because you are looking at things of zero measure. Okay. So it's yeah.
I think maybe the first people to point out this issue about reducible connections and its connection to these critical points were Marston, Abraham Marston,
Yeah.
and Moncrief and Arms.
Moncrief, yeah.
Judith Arms.
Mm-hmm.
They looked at.
That's right.
They looked at the critical points of the theory and
Yeah.
they discovered that the critical points actually occur at two places where.
That's right. That's right.
connection is
Yeah.
reducible.
So there is a general theorem people have proved after those papers you mentioned, which basically talks about that if you allow for all possible gauge invariant functionals and ask what are the common critical points of those, then they correspond to reducible connections of maximal symmetry basically. It's a very interesting theorem that you can prove. Okay. So it's not like they're ignorable completely, but I think it depends very much on the kind of formalism one is using. Okay. So in what I'm going to discuss here, they don't seem to play much of a role. Okay. And this is a bit of a puzzle for me, because since you raised the point, let me say one more thing. So if you look at 2 plus 1 dimensional Yang-Mills theory, there is an old calculation by Polyakov on how confinement can occur. Okay. Basically, he talked about SU2 gauge theory, where we know that there are, from the 3 plus 1 point of view, there are monopole solutions, but these monopole solutions are like instantons from the 2 plus 1 dimensional point of view, if you ignore the time dimension of the 4 dimensions. Okay. So you can do a semi-classical analysis of your theory, and if you do that, you can kind of show how you get confinement. The unsatisfactory feature is that if you try to take away this symmetry breaking, which is implicit in this construction of the monopoles, you lose your semi-classical validity of your semi-classical approximation, so you cannot really conclude anything. What I am going to show here today, or not today, or the next few days, is that if you look at it from the point of view of simply this space and constructing solutions of the Schrödinger equation there, you get essentially again some kind of confinement, but it's a it's very far from where Polyakov started, because he is focusing on semi-classical, which means reducible connections are important for him. For me, reducible connections are not important at all, but they both give the same result. So there is something interesting that one needs to understand there. Okay, so we don't know. That's the point. Okay. Okay. So let me say a few more things about this. So once we understand that this is the space we are dealing with, then we can now ask the question, how do I proceed? Well, we are simply going to do Hamiltonian analysis. And what are the things we need for a Hamiltonian analysis? We need wave functions. We need to know how to normalize wave functions. We need a Hamiltonian, so we need to know what the Hamiltonian operator is. And once you have these two ingredients, you have to solve the Schrödinger equation. Okay? Just everything as in elementary quantum mechanics, slightly more complicated because these are all defined on fields. Okay? But otherwise, the conceptual framework is exactly as in your first course on quantum mechanics. Okay? So how do we do that? Well, let's take the inner product. Inner product of two states will have some wave function psi 1 associated with state 1, psi 2 for state 2. So you take this and you have an integration measure. And what is this integration measure? Because the wave functions are gauge invariant, a la Gauss's law, the integration measure really means the volume element of this space. That's what you need. Okay? So we need to know what the volume element is of this space, and if we know that, then we can write down the inner product here. So the first order of the day is to construct this volume element. Okay. The second thing is we have to write down the Hamiltonian. As I mentioned before, that's E square plus B square. Electric field is functional derivative with respect to A, so it looks like this. And what is this actually? This is like a Laplace operator on the space of fields. And because we are doing gauge invariant functions, this Laplace operator is basically a Laplace operator on the space C, the same configuration space. Okay, this is like a potential energy. So this is our Hamiltonian. And so delta C is a Laplace operator. And of course, we have to construct that. Why? Because it's field theory. You have operators at the same point here. Therefore, regularization is needed. We need to go through a proper construction of the operator. Okay? This is one of the reasons why people never like to do Hamiltonian analysis in field theory, because it's just messy. Okay? But on the other hand, Hamiltonian analysis is intrinsically non-perturbative. So certain questions are best asked and answered within the Hamiltonian framework. Okay? So if nothing else, I hope you take that lesson away from my talks, that the Schrödinger representation in field theory and the Hamiltonian analysis that is entailed by this is actually useful in many contexts. Okay? Maybe I can even pause for a second to tell you the story of Feynman here. Right? Richard Feynman, you may recall, I have to tell you some of the prehistory to what inspired me to look at this problem. Okay? So some of you may be familiar, in around 1954, Feynman constructed a theory of liquid helium, which is a very beautiful, beautiful paper, where he talked about the Hamiltonian, and then he talked about properties of the wave function and the constraints imposed on the wave function because of the identity of particles, because you are talking of bosons for helium-4. Okay? And then once you have those in place, he could simply make an ansatz for the wave function consistent with that, and immediately he could at least variationally solve the problem, and he found the phonon-roton spectrum, that is the spectrum of helium-4, and here is an explanation of superfluidity. Okay? So fantastic piece of work. But in later years, in 1981, he thought he could repeat the same trick with QCD. Okay? Of course, 4 dimensions is too hard, so he went to 2 plus 1 dimensions, 3 dimensions. He tried to do the same game. Okay? And what is the essence of the argument? The essence of the argument is that if you have a Laplace operator in a compact space, it has a discrete spectrum. Therefore, you must necessarily have a gap in the spectrum. This is what he was aiming for. That's what he did in liquid helium. He showed that effectively the space relevant modulo the identification of configurations by the permutation group is effectively compact. That is what he showed. Okay. So, because it is effectively compact, the Hamiltonian has a gap, which means everything other than the phonons were excluded from this consideration. Everything other than the phonons must have a gap, which is the essence of superfluidity. Okay. The superfluidity is the statement in the spectral language that if you exclude the phonons, every other excitation has a gap. Okay. So, he thought he could do the same thing, and he tried to say that the configuration space, essentially this space I am talking about, is compact. Okay. But even Feynman has to be careful making such statements in front of mathematicians, and they immediately disproved him. Okay. The space is not compact. So, he abandoned the project. But what is important is of course, at that time we knew very little about how to construct many of these things. But what is important in many cases is not compactness or non-compactness per se, but it is also a question of the measure of things that lead to non-compactness. Okay. A classic example is a hydrogen atom, where the classical ground state is at the origin, okay. But effectively it has zero contribution probabilistically, therefore, it does not matter in the scheme of things, and you get a discrete spectrum for the hydrogen atom. Right. So, therefore, you get a gap basically. So, in a similar thing can happen in this problem. So, here again it is not compact, but what we need to do is to get a sense of the measure, which means I need to know this integration measure carefully, and I need to know this, the Laplacian, construct the Laplacian carefully to see if there is a possibility of a gap. Okay. And so, what Feynman was trying to do became possible once we could understand those two things, and that is one of the things I will explain in more detail. Okay. So, now let me I have few more minutes, right? Yeah. So, now let me just try to go on to the definition of confinement.
So far you have not actually explained what simplicity happens if you restrict 2 plus 1 dimension.
I am going to describe that in more detail. Yeah, I am giving you little by little. There are 4 talks, so it will come. I mean, the essence of the matter is, okay, since you raised the question, let me say a few words now. 2 plus 1, coupling constant has a dimension. So, I do not need dimensional transmutation compared to 4 dimensions, 3 plus 1. Secondly, the theory, there is no renormalization of E square, the coupling constant. So, that helps me avoid some of the issues that would arise in 3 plus 1. Okay. So, there are some advantages like that, and that makes it much easier. Okay. I will also talk about 4 dimensions later, and we will see that the problems that I just mentioned come back there, and we have to deal with that. That is a little more complicated. Okay. So, that is kind of the reason why, but you see it is an interesting theory in my view because of a couple of other things as well, because first of all it is the lowest dimensional theory with propagating degrees of freedom. So, it is non-trivial. It carries therefore some lessons for the high dimensional theory at least. Secondly, if you look at the Yang-Mills theory in 4 dimensions, 3 plus 1, but if you go to high temperatures, then effectively there is a dimensional reduction to 3. So, if you look at the quark-gluon plasma, there is a magnetic screening that arises because the theory is effectively 3 dimensional. That magnetic screening mass of the 4 dimensional plasma is really the gap, spectral gap of the 3 dimensional theory. So, it is not even just a model theory, it actually has a physical context, a very down to earth physical context of the quark-gluon plasma, where we can actually apply the result. Okay. So, we will talk more about that later. Okay. So, let me try to, what did I do? Oh, so I wanted to say one more thing, which is this is a statement about the topology of the space, which is that the space of connections actually is a contractible space of trivial topology. It means all the pi groups of A are 0, which is also a result proved by Singer. essentially follows from the fact that if you take the difference of any two connections, that is just a Lie algebra valued form that transforms covariantly. Okay, so it's like in a fine space. You can start from some point and then draw lines to other points on the space, and because of that, I can do an exact sequence like so for the pi groups. I just want to show you one of them. There is a lot of other topology here. So I go from pi 2 of A to pi 2 of A mod G star, pi 1 of G star, like so. Now the important point here is that the pi 2 of A is 0, pi 1 of A is 0, pi 0 of A is 0. Okay? So they are all trivial. Therefore, pi 2 of C is the same as pi 1 G star, and pi 1 of C is pi 0 G star. Okay? And these objects are related to the homotopy groups of the regular Lie group. Pi 1 of G star in 2 plus 2 dimensions would be pi 3 of G, and this would be pi 0 of G star would be again the same group. And this is either integers or integer cross integer for SO4, but for any simple group this is non-trivial. What does that mean? It means that this bundle that I talked about cannot be trivial. Okay? Space of potentials viewed as a bundle, G star bundle over C, is a non-trivial bundle. I cannot have a global section. Okay? Because if I had a global section, since the big space is 0 trivial homotopy, all the components will have to have trivial homotopy, and by simply showing that this is not 0, we show that that's impossible. Okay? So by a reductio ad absurdum type argument, we see that this bundle is non-trivial, which is what is called the Gribov problem. Okay? So the non-triviality of the bundle. Okay? So that's important, but it's not going to play a major role in much of what I'm going to say later. Now let me define what I mean by confinement after this general background. So what we have seen is that even though I impose Gauss's law to select out physical states, that still allows for charged states which transform non-trivially under the Nair symmetry G that I mentioned. Okay? So charged states are not excluded by imposing Gauss's law. So what do we mean by confinement then? It means that all physical states of finite energy for the, let's say for the pure gauge theory, have 0 charge. They are actually invariant under the Nair symmetry group. Okay. So that would be the only consistent definition of confinement, which means that any state which has charge must have infinite energy. Okay. That would be the, of course, the problem with this definition, while it is nice, precise and acceptable, it's not a very workable definition, because it's very hard to show this result. Okay. As I just say here, there are good reasons to believe this is true, but we don't have a proof. Okay. That's a big problem of confinement lying around for more than 50 years. Okay. Now, you can then ask, what can I do then? Are there diagnostics of confinement? If I get confinement in a theory, how do I know I got confinement of states? So one of the diagnostics that we can set up is the Wilson loop, which is given here by taking the path ordered exponential around some curve of A dx. Okay. It's related, the reason why this works is because it's related to the energy of a particle antiparticle pair, and here I have a short discussion of how that arises. The simplest way is to say, let's consider two heavy fields, call them phi and chi, and here is my action. All the other terms can be neglected because they are so heavy. There is no gradient square over 2m type term because m is infinity if you like. Okay. So this is all I have, and then you construct a state by creating one of each. They are separated, so you put a kind of a Wilson line between them. So this is a gauge invariant state created from the vacuum called the state f. Okay. Then if you look at e to the minus h times some time variable t here, obviously h on this state gives me the energy. So this is going to go like this: energy of the state, which will depend on the separation of these two particles, times t. Okay. But at the same time, we can do another trick, which is to say this is very much like what we do in path integrals, times the time interval t, slice it up into little bits, write a path integral variation definition of that, and that's this object here. Okay. So what we do here is that because there is a Hamiltonian for the theory, I get an action. This is Euclidean, there is no IHT here, just HT, so I get a Euclidean action, and here is the state F dagger and F dagger and F here. Okay. So if I do it like that and look at the Euclidean action for the fields phi and chi, it is just d phi d tau, d chi d tau like this, like the Schrodinger equation, just heavy particles. So it's like non-relativistic theory. That means the propagators are delta functions which go like this. Theta is a step function here, and we can then use that and simply put that into the path integral, calculate, and you find its expectation value of the Wilson line. Okay, just from the W's coming together, you can close the loop because A naught was 0. I can add that in by hand, close the loop, and get the Wilson line. So what does that show? It shows that the expectation value of the Wilson line actually measures the energy of the pair. Okay. So if the energy of and for confinement, we want the energy to increase as we pull them apart to stop us from being able to take these particles far away. That means the Wilson line should have something. If I use the Wilson line to test for it, I should be able to read off what this is. Now, of course, from actual physics of heavy quark bound states like charmonium and BB Bar states, we know that that energy connecting heavy quarks is actually linearly rising. Okay, that is the way back in 1974 when they discovered charmonium. It was very quickly realized that the linear potential gives you a good fit to the spectrum. That's right.
I just wanted to say this.
I mean, it's real physics. That's where it came from. We need guidance from experiment. Yeah. Sure. I mean, very often people say, area law, linear potential, but it's not a priori. There is no theoretical argument that gives you that. It came originally from experiment. That's indeed true. Yeah. Okay. So the important thing though is that if E goes like L, then this is L times T, which is the area of the loop. Therefore, I can rephrase it by saying that the expectation value of the Wilson line is some constant sigma times the area of the curve. Okay, that's a slightly more general way to phrase it. And this sigma is the so-called string tension. Okay.
We have a difference E of L in 3 dimensions versus 4 dimensions.
You mean in terms of area law versus?
Yeah.
No, it's area law in both cases. There's a string tension. In 2+1, string tension is a little easier to deal with because we have a dimensional coupling. In 3+1, I have to go through the transmutation process to generate a scale, and then only I can even ask the question. So the real question 3+1 would be something more like comparing two observables. For example, I can say what's the mass of the glue ball, the lowest lying glue ball, versus string tension. The ratio is a meaningfully defined quantity, okay, which is effectively saying I'm using one of them to serve the purpose of dimensional transmutation. Okay, so that's how it is. It's still the area law in both cases.
But in 2+1 dimensions, you have to make some analog of this guidance that you get from data. So are you assuming that EL goes like L in 2+1 dimensions?
That's what I'm going to assume, and I'm going to show you that. That's what I'm hoping to show. Okay, I mean, I agree that there is no a priori guidance from experiment in 2+1. Okay, but it is 3+1. This is what you would like, and it happens that that's what you also get in 2+1.
Does it follow simply from dimensional analysis because there is no other thing that you have?
You could say that, but on the problem with that is there is a dimensional parameter, coupling constant square. So it does not rule out a logarithm of E square times L multiplying things, right? For example, so that's the issue. Yeah.
So this is the definition of confinement that you're going to use.
No, I'm going to say that. I mean, this is all I can do So, in that sense this is what I am going to use. However, my next slide is going to say that this is not good enough. Okay. I just want to expose all the subtleties here. Okay. There are some things we can do, but clearly there are many issues not clear. Okay. So, people often use this, but where it fails is precisely when there are so called screenable representations. So, if I have a representation for the Wilson line, which if I multiply by adjoint several times, if it contains a trivial representation, then that representation R is called screenable, if that happens. Okay. Screenable, can be screened is okay. So, if I take SUN kind of theory, certainly the adjoint itself is a screenable representation. There are others also you can write which are screenable representations. If you take a group like G2, all representations are screenable. Okay. So, the problem with that is when you have a screenable representation, I can spontaneously create particles in the adjoint from the vacuum which can stick to my Wilson line and make them colorless, chargeless, and thereafter there is no obstruction to taking them far away because there is no charge for either of them, right. So, there is still confinement because whatever you take away is still zero charge. But the Wilson line does not show that because the Wilson line flattens out, there is no more energy needed. Therefore, this Wilson line analysis is not a sufficient analysis when you have screenable representation. So, it is one diagnostic for confinement, but it is not a very, it is an imperfect one. For certain representations it is good, but not for others. Okay.
So is this the only obstruction to having the statement that if you have finite energy, you can, I mean infinite energy, you need infinite energy to get finite charge? You had a, I mean, I'm just restating the definition that you had earlier. So is this screenable representation the only obstruction to that, or is there something else?
No, that's the main obstruction. Okay. So, we don't have a good diagnostic. It's slightly oxymoronic the way this is done, right, because think of QCD with fundamental quarks in the fundamental representation. If I have quarks in the fundamental representations which are dynamical, all representations are screenable because I can spontaneously create quark antiquark pairs and screen everything. Therefore, Wilson line is no good for that. Okay. So, Wilson line applies precisely to those cases where you do not have screenable representations, which means, so take pure Yang-Mills theory. The only physical charges you expect are adjoint and multiples of adjoint, but to test for confinement you need something that is not in the adjoint. So, the Wilson line is precisely in those representations which are not physically realized. So, it is a very funny kind of diagnostic parameter, but that is pretty much the only thing we have. There is something else called the Polyakov loop that people use for ZN invariant things, but that is a very close relative of this. So, I am not spending time on that, but it is essentially similar idea. Okay.
So basically what you are saying is that it does not cover the full possibilities.
That is right. That is right.
Wherever it works, it works.
That is right.
That is actually how one should.
That is right. Exactly. So, if you really want to prove confinement, then this is not sufficient.
This is necessary but not sufficient.
That is right. Yeah. Okay. Okay. So, so this is all true, imperfect condition as I mentioned, but nevertheless it is of some use. You can use it in various places, and in various lattice type analysis of gauge theory this is very much used actually. Okay. And here I show you just a picture of the potential energy as a function of the distance of the length, and you can see these are for various different representations of SU3 from this paper here, and you notice that they all become straight lines very quickly and showing linearly increasing potentials. Okay. So, you do get confinement in this sense. So, there is evidence for it from lattice analysis directly, although we do not yet have a.
So this is three-dimensional lattice?
This is 3 plus 1, yeah. Yeah, so 4D lattice, yeah. Yeah, that is right, yeah. I think that is right, yeah. Okay. I am trying to remember the paper, but yeah. Okay, so now I am going to how much more time do?
You can stop at any point you think is.
Okay, I'm going to say one more thing and then stop. Okay, so there is another way to think about confinement again, which is another imperfect criterion, but I want to spend a few minutes on that and then I will stop for today. Okay, so the thing is, if you look at the gluons in the theory, in the perturbative limit, they are massless particles. Okay, of course, then they have interactions and so on. So one way to think about confinement is to say that, is there some way I can exclude such massless particles? If I prove there is a gap in the spectrum, then obviously the perturbative gluons are excluded from it. Something else may be there. It's not proving confinement per se, but it goes part of the way to say that the spectrum has a gap. Therefore, what you would normally expect as the unconfined particles are gone. Okay. So can we look for a gap in the spectrum? And there is an interesting way to think about it. Again, the Hamiltonian is of this form, gradient square and a potential energy. This is the Laplace operator. And let's say we have a vacuum state which has which I write in the form e to the minus 1/2 of s. And let's say this obeys the condition h psi naught is e naught times psi naught. Okay. What we are interested in is to look at excitations of the theory. So we construct a new wave function, some excited state wave function, which is some functional f multiplying psi naught. Let's write it in this form. Okay. And we want to say that there is some eigenvalue for the Hamiltonian. So the gap or the extra energy for the excited state is lambda. So h minus e naught is lambda acting on psi. And if you have this set up, you can look at, for example, gradient square acting on this combination here, and then you can go through simplifying it. There will be commutators of gradient operators coming, and if you do that, just keep on doing that, eventually you get this inequality here, okay, which has lambda times gradient of f star times f times e to the minus s greater than this, where r mu nu is the Ricci tensor of your space. These are gradients of this s which appears in the wave function, and you have these gradients of f again. Okay. So this is an inequality that you can establish very generally for any space where there is this s in the problem, and there is a name for this combination that appears here, r mu nu plus gradient mu of s. That's called the Berkeley-Emery curvature of the manifold with a weight function s. Okay. So this is a generalization from what people try to do for manifolds without any weight function, which is what you would try to do in terms of trying to bound the Laplace operator. So this is a general for finite dimensional spaces. This is fairly straightforward to establish, very easy to do. Okay. If you do that, if you do that, then you can see that if I say that the curvature has some positivity condition like this Berkeley-Emery curvature is greater than some number times the metric, then if you just put that into the previous equation here or inequality here, you find that that is a bound on lambda, and that gives you lambda greater than 1/2 mu square. Okay. If you take what I just said here and put that weight function to 0, that's exactly the Lishner-Rovitz bound on the spectrum of the Laplacian. Okay. That is familiar from classical analysis. It's a generalization to spaces where you put an additional weight function in your integration. Okay. So this kind of theorem was, I think it's Yavo and a couple of other people at Harvard proved this more recently. Okay. So this is an interesting inequality, and you can ask, can we try to use this? In other words, can we promote all this to infinite number of dimensions, which is what we need to do in our problem, get an inequality like so, and try to prove a gap in the
Statement is that mu is greater than 0?
Mu is greater than, I mean, if, so the statement is conditional in the sense that if curvature is bounded by a mu square like so, then lambda is bounded by this. So it's a conditional statement. So you have to give me a space where this Berkeley-Emery curvature is bounded in this fashion, then I can give you a bound on the spectrum of the Laplacian. Okay, that is the statement. Okay, So if I have a space of positive curvature, this would be true. Okay. What is interesting is that this idea goes back again to Singer. He didn't phrase it quite in this fashion, but he tried to calculate the curvature of the space, and he was able to show that some of the sectional curvatures were actually positive. So it was an encouraging sign, but he could not take it to the point where he could prove that there is a gap. Okay. But the question I'm raising is, can one revisit this and show that there is actually a bound? The answer to that, I mean, I don't know the answer to that. There is some recent progress I want to mention due to Moncrief and Mundell. Moncrief is the same Moncrief who did the thing that you mentioned. And I think there is some interesting stuff to be done here, but I think the subject is too new. We don't have a clear reason yet. The main reason I mention this is because, again, it's the geometry and topology of the space. And here, for example, the curvature of the space of potentials, modulo gauge transformations, that's really determining the physical characteristics of the theory. Okay, that's an important point actually. Okay, I think I will stop here for today, and if there are more questions, I'm happy to answer. But otherwise, we'll continue next time with this. Okay.
I just have one question about the last one. This statement seems like a statement from classical manifold theory. Right?
Yeah. Yeah.
So how do you, or how does one imagine that it will apply for, say, quantum mechanics?
Right. So I have to construct. But the Hamiltonian is a classical Laplace operator on the configuration space, right? Even though it's in the quantum theory, the Hamiltonian is an operator, contains a Laplace operator on the configuration space, infinite dimensional. But nevertheless, if I can put a bound on that, then that does tell you something about the solution of the Schrödinger equation.
One imagines that one would apply this to A mod G star.
That's right. That's right. So the main issue in promoting this to the infinite dimensions is proper construction of the Laplace operator, proper construction of the curvature tensor, things of that, and G and the metric. Right. So Singer tried to construct the curvature tensor. He tried to use a zeta function regularization to define it and try to construct. He made some progress, but it was very difficult for him to prove this actually. He could not. Okay. That was again inspired by Feynman's work. A lot of Singer's work was inspired by Feynman. Didn't succeed, but by phrasing the problem in that language, he showed all the things that wouldn't work or needed more attention and so on. So in that sense, it was a very useful paper actually. You know.
So how explicitly do we need to know S in order to make?
Okay. For this argument, you can use any S in principle. What I'm hoping is that by looking at the Schrödinger equation, I'm going to give you an S at the end for the 2+1 case. Okay. Then because it comes from the vacuum wave function. Therefore, if I know S, I'm a little further ahead in terms of understanding this perhaps, because then you know what S to use, and otherwise, it's as I said, it's a conditional statement. For some S, you may get a bound. For some other S, you may not get a bound. But if you know what S is, then there is some chance. Okay. But having said that, I mean, I don't have a proof of this statement. Okay. Proving this would be quite remarkable actually, because it really proves a gap in the spectrum. Okay. I'm sorry? Yeah, I will give an explicit construction of the Laplace operator. We will use a particular coordinatization of the gauge potentials, and then I will be able to show that it is related to a current in a related Weismann-Witten theory, and in terms of that I can give you an explicit formula. Okay, I'll show you next time. It's actually a nice expression because terms in that are precisely terms that occur in the current operator product expansion of your Weismann-Witten theory. So these things get related. There are some mysteries there. I don't know why it really happens that way, but that's what it is. We have checked it by many different techniques, methods, and the thing is, then you can actually solve the problem, or solve at least partially the problem. Yeah. Okay. So, I mean, I can show you now, but I think it's better if I show you next time. Yeah.
Next lecture or the next
I think the next lecture I'll be able to show you that. Are you here next week?
No, next week. It's all right. I listen to the YouTube. I want to.
Okay. Yeah.
But you're recording it, so
Oh, okay.
before your third
Yeah.
lecture.
Okay. Listen, Justin. Let me just show you. Yeah. If you want, I can just flash the formula. Let me see if I can. This is a Laplace operator. J is a current of an associated Weismann-Witten theory. You recognize these terms are the singular terms in the OPE of two currents, and that's a regularization correction. Okay, so it's basically that is the Laplace operator on the A mod G space. Okay, how I arrive at this I will show next time, but there is an explicit formula for that. So you mean the F and so on? Yeah, it is whatever gauge group you give me. I can do it for any Lie group. Yeah. Okay. Yeah, please.
Perhaps a more simple statement that I think for many it may not be very clear why a gap is confinement.
Yeah.
So at least for many of us who grew with this perhaps know it. But
Right. Right. So the main reason why a gap means confinement is what I kind of briefly alluded to, which is that if there is no confinement, you get zero mass gluons. So there is no gap in the spectrum. Okay. So by having a gap, you exclude all those things, and you see that the first excited state must be separated by some finite energy from the ground state, and hopefully that means confinement. It's not a proof of confinement, but hopefully that means confinement. Okay. Again, an imperfect criterion like the Wilson line, but it may be of some use actually. Yeah. Okay.
you indirectly talked about it by giving Feynman's.
That's right. Yeah.
So, but
Yeah.
I thought it may be
No, I agree with you. I agree.
say it out.
Absolutely. Yes. Okay.